it's definitely not a perfect home alarm system, just 2 gates. Let's think about the logic. What's happening here? Just read it. For example, someone asks you to design a digital system, right? And there are 4 sensors being mounted to 3 windows and 1 door of the home. And there's no difference in between these sensors. So whichever one is being opened up or being broken, then it's gonna go off, right? It's gonna trigger that alarm. So the logic seems like a OR logic, right? It can be 1, can be 2, can be 3, it can be 4, but you have to output a 1 out of it. Okay, so it's an OR logic. And so what is this one doing? Yeah, it's like enable. So keep in mind, whenever we do AND gates, we always, a lot of times we use AND gates, one of the inputs of the AND gates as an enable pin, so we can turn it on and off. Okay. And the second one, very simple. So you have to implement this on FPGA, on the basic 3 board. So design a logic, which is here, okay, and make the connections to the test bench. Things here. Sometimes I call it top because that's the top module which wraps up all the internal modules, like a top module or test bench module. So you can see top, which is the test bench. And is this a simulation file or is it an FPGA file as a top? Could you tell? Yeah, but is this a FPGA implementation or it's going to be a simulation only? And why? There are just 2 files, nothing else. That's the whole design. And this is from the logic gates, right? See, 1, 2, 3, 4, and OR logic in between an AND gate to the M enable pin. And a sign statement? No. Could you tell? Is it just running on Vivado or is it being implemented to FPGA? And why? Why?
I mean, it doesn't know anything about the board here.
But if you're doing it in Vivado, you need a timing. But we don't have the timing here. You need like 20 seconds. So remember the keywords SW and LEDs are in the constraint file. Have you used the constraint file to do anything? In the lab? Have you? You haven't implemented anything on the board. So probably it's a lab on Thursday. So the switch, SW and LED, these are actually the physical pins on the FPGA board. Just keep in mind. So when you work on this project or this assignment, you have to load that constraint file which has all these the keywords and also the physical pin numbers on the chip that which are being connected to where, right? So specify that in that constraint file. So you load that constraint file to Vivado, and then it's going to recognize that SW is a switch. I didn't put a length in the front, or prefix in the front. So by default, it's going to be a 16-bit switch. So SW has 16 bits in there. That's what you already defined in the constraint file. Same to the LED. If you look at the board, there are 16 little tiny surface mount LEDs on the top of each switch. So this is 16-bit as well. Okay. And now 420 means I have how many switches being used as an input? 5. Why switches are input? You switch on and off, then you give an input, right? So LEDs are input or output. Output, you cannot, it's just showing, displaying, so it's the output, okay? So why is 0 to 0? What does that mean? It's just 1 bit, so it's 0 to 0. It's very odd way to do it, but just keep in mind, if you just need 1 bit, just do 0 to 0, and 0 that might work as well. You can try it. Yeah. And then have this unit under test here and make the connections. Okay, and you can use just part of it. So from 3 to 0, just keep in mind when you declare it, you want to use a prefix. But when you use it, access the certain number of bits in there, you need the prefix. How to say it? Yeah. So 3 to 0, the 4 bits switches being shorted to S as the 4 inputs, the door, and 3 windows inputs, and 1 switch as enable pin. So I have to switch it on in order to enable the system. So that's a very simple combinational logic module. And it's going to work on FPGA. And there's another, so I shows you all the steps. See here, you add the sources to Verilog, to Vivado, and here's a constraint file. Also add it as a constraint file source, and run synthesis, run implementation, and generate the bit stream, and eventually open the target and upload the code to the board and demonstrate it. Okay. And this is a password system. It's called digital safe system. Also very simple combinational logic, no sequential logic, just the static gates. So P0, P1, P2, P3, these are given password, just 1 zeros. And the S0, S1, S2, S3, that combination, the 4-bit binary number has to match with the existing password in order to turn on I/O. And now let's look at the logic, see if that makes sense. These are XOR gates. So what's the logic for XOR gates, remember? The 2 inputs has to be what? Then you are getting a 1. For XOR, exclusive OR, right? They have to be different. They have to be different in order to get a 1. If they're the same, doesn't matter if they're both zeros or both ones, you're getting a 0 output. So that's why we only use a XOR gate here to match the 2 inputs. If they match, if they're same, which means that I'm putting a correct password in there, right? Then I'm getting a 0 output. So 0 will be inverted. I give you a 1. So I have to have all 1s for the AND gate in order to get a 1 for I0. It's going to turn on one LED. So whenever you get the password, so think about that. How do you implement it on the FPGA when you're designing this very simple system just for fun, for high schoolers, right? 2-minute demonstration for beginners. When you demonstrate on the FPGA, so what you have switches, and you have LEDs, and you have an FPGA board that you can implement that logic. So whatever, just in here, a circuit into the FPGA chip, right? So how do you want to demonstrate it? Let's see if the input password already given or not. So see here, it's a parameter, it's a constant. So in the design, I already give that 0101 as a password already programmed in there. So I have to use my switch to match it in order to turn on a one LED. So this is to let you know that you can have a parameter set up or constant set up in Verilog in this way, right? So 3 inputs, the switch, 4 inputs, the switches for the 4 password for the user, and 1 output. No, two output, because it has 1, just 2, just adding an inverter to it. Why they do that? Why they added an inverter to it? If you put a wrong password, I1 will be always what? On, right? So since you have 2 different outputs. Yeah, so so I1 is telling you that there's a 0 at I0. Otherwise, you're thinking like the board is not powered up. It's just nothing. Okay, which means I just want to show you that it's outputting a correct value there. It's 0. It's not like 2.5 or just a floating voltage. So what's going to happen is when you are outputting when you are inputting a wrong password, this will be always on and this will be always off. But when you get a right one, it's going to flip, right? It's be 1 0 instead of 0 1. Okay, so whatever. So that's why we had two outputs, 1 to 0 for the LEDs. And here's the logic. You can just follow the circuit to from the logic, and that's the test bench. Test bench is, again, this is based on FPGA. It's not a simulation because SW is a switch, LED is a LED for the keywords for the FPGA for the constraint file. So I'm using 4 switches and 2 LEDs, and here's a connection. So here, that's how I can run that demonstration. Okay. And this is a car parking occupied spots counting system. Okay. We have seen some of the dashboards showing how many empty spots still available in the parking garage. Probably have seen that somewhere. Outlets in the big cities. You park in the garage, you'll see but sometimes they show you a number on it's usually the 7-second display numbers like 20, green color, 28, like parking spots available on floor 1, and sometimes they have an IR sensor on the top of each spot, so you can see that, right, green or red in a row. You'll be able to tell like which one is still available, so you can just drive there and take it. Right? But it's not an indicator LED for this simple design. It's a counting system. So it just uses a very simple truth table. So for example, if it's 0, 0, 0, then which means 0 outputs, right? So 0 spots available. Okay. If it's 0, 0, 1, which means 1 spot available, right? 0, 1, 0 is still 1. How these numbers are being retrieved? Where can you get the 0, 0, 1, 1, 1, 0 number from the parking spot? Yeah, how can you get it? So this, for example, you get this, you need a person to count and then put it. All right. Someone is going to do that, right? Paying $50,000 a year just counting. They have to run really fast because the spots are being taken really quickly and cars are leaving really quickly. You need a sensor. Just put a sensor on the top, right? So the sensor is gonna, IR sensor, if the car is there, is blocking the IR light. So your receiver at the bottom is not receiving any light, like a garage sensor, right? You got an emitter, got a receiver. If it's even blocked, then you got a different signal. So that one will send the signal to probably to somewhere. Can be a microcontroller in the middle, like a hub. So that one will process it as. So this is what the circuit is going to do, right? Just processing and output how many spots are still available, right? So these 0 and 1s can be the output from the sensor. If it's being taken, then the receiver has a different signal. It's outputting a different signal to the microcontroller. We don't even have a microcontroller here. It's just a very simple conventional logic, right? And still can do the job. Not ideal, but can still do it. How? Let's just design the truth table, right? If I have 3 zeros, then it's 0. If I got 2 0 and a 1, I just output a 1. And so on and so forth, right? If I got 3 1s, which means I got 3 available. Okay, totally customizable. And after you got this truth table, what's the next? So we are designing a combinational logic circuit out of this truth table. So we don't have any microcontrollers, assuming that we don't have it. It's not like a C language, like software. Input is it. If the input is this, then do this, right? We don't have it. It's just totally hardware. There's no C language. Totally digital circuit. How to design a digital circuit from the truth table? Is it following every column? Because these are two different outputs. I understand that it's been a couple years from logic, digital logic. So when you design the digital circuits, you look at each column at each time. Okay, look at C1 first, right? We need a digital circuit to get C1 out from these inputs. And then we look at the ones, right? And then we find out the min terms. So for this term, it becomes what? Let's see how I can type it here. Just, okay, for the first one here, it becomes S0 and, oh no, S0 not, right? And S1 and S2. This equals what? C1. That's the circuit. You got 3 inputs and 2 AND gates, maybe 3 AND gates, 2 input AND gates, right? So you can get C1. That's not right. That's just one min term. And you need a second one, which is S0, S1 not, S2, or this one, right? The bottom two min terms. And then eventually all these things equals C1, and just do the same thing for C0. So that's how you can get the logic functions for C1 and C2, and then form a digital circuit out of it. Okay, that's how you get it here. You just type it in Verilog to form the logic you have here, and make a top module and put in to FPGA to demonstrate it. Okay, these are the second half of the tutorial in addition to the data types, the floating numbers, the floating point number, fixed point numbers. Any questions on this by far? This is due Thursday, at the beginning of the class on Thursday. Doable? Okay. Now let's look at the lab. So is there anything I've covered for the lab? Are we at lab
2?
3? Okay. Yeah. Yeah, I'll add a little bit some new things to it because this has been used for the digital logic class as well. Very doable, very fun lab to work on. All right, I'm gonna give the rest of the time to you guys to work on the tutorial. Okay. We don't have a quiz this week, so no quiz this week.